This is the new serial interface on PlasMa version 6.6. Thanks to a suggestion from another PlasMa owner, shout out to Matthias, the dot matrix printer socket can now be used as a serial interface supporting the SPI protocol. And this old school meets new school feature opens up access to a multitude of modern devices. Now, don't expect miracles. The SPI clock only runs at 770 kHz, so running Doom on an external terminal is not on, but I'm sure there are plenty of other applications. These are the pin mappings. The 9 outputs and 2 inputs are designated as auxiliary to show that they can still be used for general purpose, but the internal hardware is unchanged. All I/O pins are buffered using 74HC4050 chips running on 5 volts, so outputs are 5 volts and inputs can be up to 15 volts. The only changes are in the firmware, and new system functions are available in the Plex and Forth emulations. Outputs could be set or reset individually using aux write high and aux write low, and inputs can be read individually using aux read. The only SPI function is called transfer byte, and this sends and receives a byte of data in a single operation using 3 of these aux pins. Aux out 0 for clock, aux out 8 for data out, and aux in 0 for data in. Now, this arrangement allows you to allocate any unused pins however you like. For example, outputs could be individual chip select signals if your device needs them, or if you want to drive multiple devices. Or you could use them as reset signals for 4-wire SPI devices. Another use is for controlling power. Some devices get in a knot if the SPI signals are not in the right state when they power up. And unused inputs could be used to monitor various states from your device. Okay, that's the theory. Here's a practical demo to test data output using a MAX7221 LED driver chip. This uses SPI and can drive up to 64 LEDs. I'm using an old PlasMa status board which contains one of these chips plus a few LEDs, so this should be good enough for the test. I'll be using Forth for convenience to call the system functions, but you could do exactly the same using Plex machine code instructions. The red and black wires provide power from an external 5-volt supply. The green wire connects the supply's ground to PlasMa's ground. Yellow is the SPI clock, brown is data out, and blue is the chip select, which I've chosen as aux out 1. Now, I don't need data input, so aux in 0 is not connected, and this means the pin can be used for other purposes along with aux in 1. Now, first I'll define some Forth words or routines to select and deselect the chip. Chip select, aux 1, and the system function is SP aux write low. And conversely, chip deselect, aux 1, and write it high. I need to initialize the other SPI pins before using the transfer byte function. The interface uses the mode 0 variant of SPI, so the clock signal needs to be low. So aux 0, SP aux write low. The data out pin needs to be high, so that's aux 8, SP aux write high. And finally, the chip select pin needs to be high, so I'll just run the chip deselect routine. Right, we're now ready to use transfer byte, but what do we transfer? Well, this is the tricky part. The function knows nothing about this chip. it just sends and receives bytes. So you need to do some research. Now some devices are fairly easy to drive, and others, like display screens or Wi-Fi devices, can be very complex. Now you could search for code libraries online to get some ideas, but bear in mind that some sources are not reliable and may be out of date or just plain wrong. Very few sources bother to add dates or version numbers. The vendor's datasheet is usually the most reliable reference, and you'll learn far more about the device from these than if you just blindly copy someone else's code. Just be patient and methodical. Okay, back to the chip. A common interaction is a 2-byte transfer comprising a command byte and a qualifier byte. So I'll define a routine called send command, which takes the command and qualifier from the stack and sends them over SPI. So send command. First we select the chip. Then we do the transfer for the command, which is SP transfer. And we need to drop the return value. We're not interested in it. Now for the qualifier, same again, SP transfer and drop the reply. And finally, deselect the chip. That's it. Now the chip has a handy command called display test, and if we can send this command correctly, all the lights should turn on at maximum brightness. The datasheet says the value for this is 15, but I'll give it a name for convenience. So we'll call it test, and it's the value 15. I can now start the test using a qualifier of 1. So drum roll please. 1, test, send command. And there it is. You can stop it with a qualifier of 0. 0, test, send command. Okay, this simple test shows SPI must be working, or at least the output is. So I could stop here, but if you're interested in turning individual lights on and off, stay tuned. Now, the chip contains several configuration settings which are initialized at power on, but some of these need changing before you can use it. I'll define some more command names and values as before and explain them later. There's one called scan limit, which is 11. One called brightness, which is 10. One called shutdown, which is 12. This is just a subset, but it's all I need for the demo. Now the chip is designed for driving up to 8 7-segment displays, or digits, and each digit can have a decimal point, so there are really 8 segments, or LEDs, per digit. The scan limit setting tells the chip how many digits to display. They're numbered 0 to 7, and the scan limit is 0 at power up, so the chip will only display digit 0. Now I need to access digit 6 for this board, so I need to increase this. So we say 6, scan limit, and send command. Now the display is disabled at power on, so nothing lights up, but the segment states are held in a static RAM inside the chip. And this may contain random values at power on, so for a tidy startup we should turn off all segments for all digits before the display is enabled. The digits are set using the same send command routine as before, except that the command is the digit number plus 1, so this goes from 1 to 8, and you may have noticed the previous configuration values were greater than 8, so there's no clash. The qualifier is the digit value, where each of the 8 bits corresponds to a segment, or LED, within that digit. Now that plus 1 can get a bit confusing, so I'll define another routine specifically for writing to digits. Write digit, have the one here, and then call send command. Now this adds 1 to the digit number before calling send command, and means I can stick with the 0 to 7 digit numbering convention. So to clear all digits 0 to 7, 0 is the value, 0 is a digit, and we call right digit. Again, 0 for digit 1, right digit, and so on. Okay, one more adjustment, the LED brightness. I can do this at any time, but I'll do it now so I don't forget. The brightness value is set to minimum at power up, but I want to set it to maximum so the lights show up better on the video. The qualifier range is 0 to 15, so I need 15 brightness. GHT send command. This would draw more current from the supply, so you may choose to lower this in practice depending on how many other digits are in use. The total maximum current is limited by a resistor. I won't go into details, but I can recommend reading how the chip scans the LEDs and pulses them on and off. There's some clever stuff going on behind the scenes. Right, now to turn the display on, and up to now it's been off as the chip powers up in shutdown mode, and the only way of seeing any lights is by using the test function, which we've already seen. So to take it out of shutdown mode, you need a qualifier of 1. Now this caught me out first time round, as I thought 0 would be more logical, but that's what the spec says. So 1, shutdown, send command. A qualifier of 0 shuts it down again, and you can do this at any time to blank the display and conserve power. Okay, we're finally ready to turn individual lights on, but first I need to explain how the digits and their segments map to the LEDs on this particular board. Now this is just down to the PCB tracking, and my priority was for simple signal paths as opposed to a logical layout, so I rely on the software to sort out the mapping. Only 4 digits are used, but they are digits 0, 4, 6 and 2 from left to right. This diagram should clarify things. The least significant segment of each digit's value is on the right, but not all segments are used. So to turn on the rightmost LED, I need to write a 1 to digit 2. That's the value, digit 2, right digit. To turn on the rightmost 4 lights, I need a value of 15, which is binary 1111. So 15 to right digit. And how about all 8 lights? And that's 255, digit 2, right digit. Now you may notice some lights are brighter than others, so be warned that different coloured LEDs have different relative brightnesses. This is nothing to do with the chip. It drives all LEDs with equal currents, so you can either avoid mixing colours on the same chip or add current limiting resistors to the brighter ones. I ended up scrapping the multicolour version and made a new board with red LEDs. Let's try the next set of 8. This is digit 6. So we'll have 15 to light up 4 segments on digit 6. Okay, let's turn them all off. 0, digit 2, right digit, and 0, digit 6, right digit. And finally, a simple loop to cycle through the 8 rightmost LEDs from right to left. Define test. Let's clear the screen a minute. Right, define test. I'm going to put 1 on the stack, and then I'm going to write to digit 2 and multiply the value by 2, which will give me the next LED, and continue to loop until we've done all 8. Don't worry about this code. Right, T. I'm not sure if the camera caught that. I'll do it again. I'll make another test to loop this forever. Define test 2. That calls test, and then jumps back -4. Right, test 2. Okay, that's it. The new version of PlasMa and documentation is available on the Philizone website, so thanks for watching.